Alright, in this next video we're going to begin our discussion of E2 reactions. Remember, in the last video we discussed SN2 reactions. Okay, that was a concerted mechanism. Now we're going to discuss E2 reactions, which is also a concerted mechanism. We're going to bring all of this together at the end of the chapter where we compare SN2, E2, SN1, and E1. Okay? So just as a brief introduction to E2 reactions, what we have is an alkyl halide here. And this alkyl halide has to have at least 2 carbons for this to work. So we've got a halogen attached to one of the carbons, and we have to have a hydrogen at the beta position. So the alpha carbon bearing the halogen has to have a carbon next door that has a hydrogen. So this is called beta elimination or 1,2 elimination, and our product is an alkene. So what happens is the base pulls off a hydrogen, okay? We form a double bond between the alpha and beta positions, and the leaving group is kicked out, and this is a concerted mechanism with those 3 reaction arrows, okay? And we get an alkene plus the conjugate acid of the base plus the leaving group. So let's identify our players again here. We've got our alkyl halide or substrate. I didn't write that correctly, did I? Okay. We've got our base, which is often abbreviated just as B dot dot minus. And that's going to be a pretty strong base for this to work. And then we form our product, which is an alkene. Okay, we get the conjugate acid of the base and the leaving group. I can't write today. Leaving group, okay? So this is called an E2 elimination reaction. So this is an elimination reaction because we're eliminating the leaving group. We're pulling off a hydrogen in the leaving group, okay? So we've got a proton transfer and loss of leaving group in this one concerted step. So the kinetics of this reaction is very similar to the SN2 reaction. The rate is equal to some K times the concentration of the alkyl halide times the concentration of the base. E2 stands for elimination bimolecular because there are 2 species involved in the rate determining step. Okay? So what about the substrate? Let's consider a reagent such as sodium hydroxide, which is a strong nucleophile and also a strong base. Okay, so this could, potentially do substitution reaction. It can actually come in here and attack at the alpha carbon, kick out the leaving group. But the fact is, if we've got like a tertiary substrate here, then it's not going to be able to reach that alpha carbon. It's going to be, bouncing off basically. But remember, if this is a tertiary substrate, then each one of these alpha carbons has got, say, some hydrogens on it. Sorry, beta carbons. Has got some hydrogens on it. And those hydrogens are sticking out. So the hydroxide can actually function as a base and a nucleophile. So the beta proton can be abstracted even though the substrate is tertiary. So the fact that the substrate is tertiary does not hinder the rate of an E2 reaction. In fact, it actually speeds it up because it stabilizes the transition state of that reaction as this reaction is occurring. Okay, it stabilizes the transition state, which is going to look like we've got our base pulling off a hydrogen. So we're breaking the bond to the hydrogen. Okay, and we're forming that double bond Okay. And kicking out the leaving group. Okay, so our transition state looks like this. And so the tertiary substrate is going to be donating electron density in and stabilizing that transition state that occurs in that occurs in this reaction. So what does our energy diagram look like? Very similar to the SN2. We've got energy versus progress of reaction, and we've got our starting materials going to products, where we're going through that one reaction hump, and our transition state is right here at the top. So just a one-step mechanism where we're, let's go back and look at this again. We've got, let's just do this one. We've got hydroxide acting as a base. Okay, let's use this alkyl halide here. So for the E2, okay, this is going to pull off a hydrogen, and this bond that was attached to the hydrogen is going to form a double bond here. Okay, so those two electrons in that bond are going to form a double bond between the alpha and beta carbons, and the leaving group is kicked out all in one fell swoop. This reaction happens in a one-step mechanism, so we have this one-step energy diagram. Okay, so in the next section we're going to discuss naming alkenes.